Now we're so much done with functions. Let's head into limits and continuity. By far, limits and continuity are one of those few topics that are easy, yet these are extremely confusing. Well, of course, if you're just starting to understand limits and continuity. In my previous experience, although the questions were really easy, students weren't able to find the answers easily, probably because the confusions are not yet dispelled thoroughly. So right now, we'll be discussing about limits, and we will tackle all instances where there are a lot of confusions that come into mind. With that, let's first define limits given by the reference that we used in calculus. So it says here that if f of x, which means that's our function, and in this figure, f of x is the function right here in the red one. If it becomes arbitrarily close to a single number L, so we are referring to the number L in which we have a value of y here. For example, the value of y here, say 4, just assuming it is 4. So we're referring to that number. And such that x approaches to c from either side. So in this case, c is a value of x. For example, x has a value of, let's say, 8. So we're referring to x approaching from either side. We do have two sides here, the right and the left side. So if it approaches to both sides, then the limit of f of x as x approaches to c is L. So I think it still steers more confusion, so let's just make it more clear. What we mean by either side of this is that in evaluating limits, we have to consider a right hand and a left hand. So as you can see here, the arrow from this portion at the right is what we call the right. Let's just use black pen here. So this means that this is the right side. So this is the right side, and this one is the left side. So with that, the easiest way to identify the right and left is that if you have a certain number here, let's say c. So the best way to be able to identify the right side and the left side is just to think of that number, and in this case we have c, and then any number that is right of c is actually the right side. And that goes the same way for our left side. Any number that is left of c is the left side. So in that case, we are referring to all the numbers that will approach c from either left or right. So let us simply give some example of the right and left side numbers. We can generally prefer a right hand side of a number as the number and then just a positive superscript, and of course the left would be c negative. So this doesn't mean a carbon with a positive cation or so. This simply means that I'm referring to any number that is at the right of c, and this one is any number that is at the left of c. For example, as I've mentioned before, if c is equal to 8, then c plus can be 9, 10, 11, 12 to any positive infinity. And it is also true for any rational number. For example, I have let's say 19 over 2, so something like that, and then 8.00001 also qualifies for that c positive, because since 8.0001 is greater than 8, then that is also at the right of C. And then the same thing goes for C negative. So 7.999 and all the number 9s that you can give here would be the very close number to 8 in terms of being at the left of C. But this is also true for 6, 5, -1, -7. So these numbers are all at the left of C. So with that, if x approaches from either side, either from the right and from the left, if it has the same value for our function, in this case, if it approaches from right to left, it will trace the equation and then it goes downward and then it will have this certain value here. If it approaches from right going to left, then it traces this curve going upwards and then it will have the same value. If the limit has the same value, then we will call this, of course, the limit of the function. So just to make it clear, the limit of f of x as x approaches to C is equal to L. So this is true in this case if and only if the right and the left limit have the same values of limits. In this case, if we have C here, we are actually referring to the limit of f of x as x approaches from C positive, and then limit of f of x as x approaches to C negative. So in this case, we have to remember that this should be equal to L, and with that, we do have a limit. In short, say, dapat pag mag-evaluate tayo ng limit, the left and right hand limit should be equal para masabi natin na meron limit. If not, then the limit does not exist. So that's a simple thing that we need to remember about limits. And there are still limits na nag-exist by just having the right hand or left hand. For example, this limit, let's say we have the limit of, let's just give an example, x squared, and then x approaches from 2 positive. So in this case, if we want to find the value, so we are referring to we are referring to the limit of x squared as x approaches to 2 from the right side. So if we wanted to graph this, so x squared would have a graph like this, and then so this is x squared, and then if you're talking about the limit of x squared as x approaches to 2 from the right side, then this is 1, 2. So this is 2, and then the x will approach from the right side. So we're technically referring to what the value of function is here. From the right of 2, and then tracing the curve downwards. And of course, it depends upon the curve. If the curve is something like this, then the graph will be traced like this. You just have to follow the direction of our x. Okay? And in this case, this is called a right hand limit, as what I've mentioned before, and referring to this, the designation for all the values of C that is at the right. And if this is negative, then we call this the left hand or the left-sided limit. So with that, if we do have only equations like this without any symbol at the top, at the superscript, let's say for example it doesn't have any positive or negative, then we are referring to these two. It is both positive and negative. Okay, so when we simply say the limit, then we're referring to that positive and negative, the right and the left hand side of the limit. And usually if an equation says that you need to find the right hand limit. So basically, we're referring to that to the positive superscript here, and that the same thing goes for the left hand limit. Okay, so that's how it goes for our limit. So remember, the limit or the two-sided limit only exists if the right and the left hand side of the limit exist. If any case you're given the equation in which you just need to find the right hand limit, then you don't have to find this limit here. You just need to find the right hand limit or the left hand limit if that's what the problem asks you. So with that, let's try to evaluate other limits that could exist in such a way that it's not the right and left, but it becomes more complicated when we get to know this stuff. Now, remember, limits are those that approach to a certain value at a certain number in which our c here approaches from either side. And as we can see here, f of x, the graph that is colored red, we can see here that if we wanted to try to evaluate the value of f of x as c approaches from the right side, so don't mind this left side, from the right side we could see that the value of y is simply increasing indefinitely as the value of x comes close to c from the right side. To give you an example, let's say at 0 it is, let's say 1, 2, 3, 4. So let's say at 0 we have 1, 2, 3, 4, 5. We have 5, and then around -1 we get something like 7. So as we come very close to this value of c, what we get here is simply a very, very high value of y, since this is an asymptote of this function. So with that, we can simply say that the limit of f of x as x approaches to c from the positive side would give us a value that is not a number, or meaning has a value that is very large. And in limit, we say that a limit exists only if there's a single number that can represent it. So in this case, the limit will not exist. In mathematical term, and we're talking about improper limits, we can represent this as positive infinity. But for now, we can just consider it as something that we call an improper limit, because it doesn't approach to a certain value or a number. And for this case, I'll just add some positive infinity here just to make this make the equation final, or the solution. But technically, we're talking about improper limits here. And if you're asked to solve for this, I would rather say that you write the limit does not exist rather than writing it as positive infinity, because we will have a separate discussion regarding improper limits, or improper limits, or infinite limits. Okay, so the same thing goes for the the left hand of our limit. If we say that the limit of f of x as x approaches from the negative side on the negative hand, then we will say that this will have a very large value of y as it comes closer and closer to c from the left side. But we can identify what that particular large value is, kasi hindi naman natin talaga ma-identify kung ano yung value nun, kasi diretso pa yan dyan hanggang baba, kasi since siya ay asymptotes, diretso lang yan. So with that, so the limit also does not exist. And to give it to give an answer in a mathematical way, we could simply say that this is a negative infinity. But as what I've mentioned before, I don't need to see this something like negative infinity or positive infinity. I just need to see this term. It doesn't exist. Okay, and with that, if we need to find the limit of f of x as x approaches to c, so the difference between this limit of f of x as x approaches to c from these two here is that I am referring to the right hand limit and the left hand limits here. But in this case, I'm referring to the two-sided limits, meaning this should be something like not a combination, but in consideration with the right and the left hand limit. And to be able to solve for this, the values of the right and the left hand should be the same for me to give an answer for this limit of f of x. In this case, if you would try to consider the answer that it does not exist, the answer should be does not exist because they are technically the same. But of course, this is a verbal. This is a word, not a mathematical answer. And let us consider this positive infinity and negative infinity. In this case, positive and negative infinity have the same. Have different values. So with that, if they have different values for the right and the left hand limit, then we can simply say that the limit does not exist. So it still makes sense that the limit does not exist. Okay, so with that, improper limits are usually those limits that involve these infinities or this stuff that goes very, very close to a certain asymptote, but it doesn't touch it, and then you can't definitely find a certain value for that. Okay, and then if this one doesn't exist and it is considered or classified as an improper limit, how about this g of x? Now let's try evaluating this g of x. We need to find something like the limit of g of x as c. Now take a look at this arrow here. We usually write c or we usually write the arrow as if it comes closer to c in either right or left hand. But in this case, as you can see here, the arrow actually goes away from c rather than coming closer to c. So with that, how do we express this as x? How could you simply express these in terms of an approaching value when x is not approaching to c, but it's like going away from c now? It doesn't, you don't have to express it something like this. That doesn't work that way. But what we need to understand here is that the values here, for example, I have, let's say, 5. Then this becomes 6, 7, and this number line would extend indefinitely to that very large number, and somehow it will approach to that very, very large number called positive infinity. So with that, I can simply say that this approaches to positive infinity, not c. Okay? Remember, the arrow is just like going away from c. And these are called improper limits because we're not considering a certain value of c in which we approach either side, but we're referring to a certain value where x can approach. We're referring to a very large value where x will be approaching. Okay, so with that, that's how we will write this one. No, and then if kung mapapansin nyo na yung c natin is it goes to it will become a very large number. The function g of x, the arrow is here. So san kaya siyang value lalapit with that case? Diba? If it comes very, very close to the x-axis but won't be touching it, it still makes sense na it will come very, very close to the x-axis but it will not touch it. In this case, the answer should be 0 because technically we're approaching y equals 0, but of course it doesn't need to touch it. Remember, limits doesn't have to touch that certain value in order to have that solution. you will encounter a lot of those kind of problem na hindi naman talaga siya yung belong dun sa equation na yun, or we call this the discontinuity, but it is still the solution of that problem. So in this case, we can see that it comes very, very close to 0, but it doesn't touch 0. So the thing is, limit is not actually the function itself, no. Limit is something na parang behavior yan ng ating graphs na kapag ka-check mo, kung lalapit naman siya doon ng lalapit indefinitely, then that's the answer. So that's how limits differ from a function. I mean, by just simply solving for a function. So with that, the two improper limits that we have are those that approach in either side, but the function is asymptotic, and then those that approach to either the positive infinity, and then of course if this arrow goes to the left, then this one's referring to the negative infinity. And in this case, if you would ask me what is the answer for negative infinity, then we can just the answer would be it doesn't exist, because technically if it is from negative infinity, we will have to have this kind of values here, and it extends indefinitely to positive y. So most probably I would say that it is positive infinity, but in cases where we're just introducing limits, I would say that it doesn't exist. Okay, so later on we will have a lot of problems for you to identify what should be the answer for such kind of problems. Okay, so I hope these two examples make it clear about limits. Just be reminded that about this definition that you need to have either side of the equation approaching to a certain value, and whatever the value is at that y value, for as long as the curve traces in such a way that both sides of the equation come close to that value of L, then that's the limit of that function. Okay, so now let's talk about the non-existence of limits, because most of the time, or not most of the time, but sometimes limits do not exist. And these three examples are the basic examples that why limits do not exist. So the first one, if f of x approaches a different number from right side of actually this should be right side of C. Sorry. So if f of x approaches a different number from the right side of C, then it approaches from the left side of C. I forgot to write it, sorry. So with that, this is C. And then if, as what I've mentioned before, if we're talking about simply limits, we're talking about the two-sided limit. And in this case, if I wanted to ask you what is the limit as f of x, what is the limit of f of x as x approaches to C, then you would see that in the right side, it approaches, the limit approaches to tend to go to 1, 2, 3, 4, positive 4. Now, from the left side, what we have here is around negative 3. So with that, since the limit of f of x as x approaches to C from the positive side, what we get here is a based on this based on this 1, 2, 3, 4 graph, assuming that I have made the correct intervals, we have 4. And then for our left hand limit, you will get negative 3. And since these two are not equal, then the limit does not exist. That's why that's the first one. This is somewhat like a piecewise functions, and usually the piecewise functions, if you're asking for the limit in which there is a gap or a jump, then probably that limit won't exist. Now, for the next one, for number 2, if f of x increases or decreases without bound as x approaches to C. This is actually the example I have given before. It looks like one. So if we're referring to the limit of f of x And in this case, if I want to make an equation, then x approaches to c positive, since this one just goes from right to the left. Okay, so with that, what is the answer? So the limit does not exist because the y value here will just increase indefinitely as our value of x approaches to this value of c, and with that, the limit does not exist. And you might be wondering, why don't I have to solve for the negative, x approaches to c negative? That's because this equation is actually asking for the right hand limit only. So remember, if the equation has two arrows, then probably it asks for the two-sided limit. But for this one, it does have only one, or the right hand only. Now this one, number 3, this is a much more rare cases, but if f of x oscillates between two fixed values of x, two fixed values of it should be two fixed values of y or L, something like that. Let's just use y. Two fixed values of y as x approaches to c. So in this case, as you can see here, we have c, and this is a very rough graph and a very crowded graph. But the thing about here is that when we come close to c, what we have here is just the graphs just keep on spiking from the upper and lower value. So remember, what we need to have in limits is that something like a steady trace of the graph, and then it ends up to somewhat a value of y. But in this case, if you wanted to try to pinpoint a value here, you can actually not trace it because it is overcrowded with a lot of oscillations, and that's the case when the limit doesn't exist. If we have already discussed about the calculator techniques involved in this scenario, you would realize that you're really having a lot of hard time finding the answers, because the calculators would just give you a lot of numbers, negative, positive, and you can't easily determine what is the value of that function. So with that, the limit doesn't exist for those cases. Okay, and of course there are just few examples of this, and the good thing about it is that I won't ask you to graph the functions, and graph the function, then find the limits using graphs. So I don't do that in class. So these graphs are actually an aid for you to understand limits and how it works. So with that, finding how limits exist and how limits do not exist, let's move on with some items in your handout that I've given you. I hope you're reading this, and we can now proceed with how we evaluate limits. So I've actually hidden a lot of points here just to give you some thrill. Well, anyway, let's proceed with all the properties and how we will evaluate these limits. The first one is that the basic limits. When we talk about basic limits, we're just referring to these properties here that are stated under the basic limits. We generally have 3. So the limit of b is equal to b as x approaches to c, and then the limit of x as x approaches to c is c, and then the limit of x to the n as x approaches to c is equal to c to the n. So this is a very simple example. If, for example, I have a function that is a constant function, so I would say, for example, that the limit, I would need to find the limit of, let's say 4. Our function is 4. Let's say we have f of x equals 4. And then I would want to find the value of the limit as x approaches to 2. So based on our basic limits and the rule here, it says here that the answer should be 4. And it makes sense because if you have a constant function, as what I've mentioned before, if this is 4, 1, 2, 3, 4, then the straight line, if you would approach to to a value of 2, 2 is right here, either from left or right, what you will get is simply the value of this function, and that is actually equal to 4. So that makes perfect sense, and it is also the same for any function that is given as x. For example, I have the limit of x. So that makes perfect sense, because what we'll do here is just we need to substitute this value for our limit, and that is equal to 2. Because f of x is equal to x, that simply is a line that is drawn with the mirror of x is equal to y. So whatever the value of x here, then that's also the value of y. And then for number 3, it's just something like an exponential function. So if we have, for example, the limit of x to the 4th, and then we need to find the value as x approaches to 3, then what we need to do is simply substitute this value with the equation. So we get 3 to the 4th, and I will not be evaluating this further. But in the exam or in your activities, you need to give the value of this. Okay, so that's all for our basic limits. So remember these 3. Whenever you have a constant, whatever the value of the limit is here, then that's just simply the answer. I mean, the answer should be the function itself. And then for any function that is x, so when you're approaching to any value of c, then that's actually the answer. And the same thing goes for our number 3. Okay. So with that, let's try taking a look at the second example. Okay, so now let's try having these properties, or the basic properties that we have in limits. So we're given with 2 limits here, the two functions actually. We have f of x and g of x. Both of them are approaching to c, and then of course they will have different values of the limit L and K. So the scalar multiple states that if a limit b of f of x as x approaches to c is evaluated, then the limit is b of L. B times L. So b here is actually a constant. For example, the limit of 3 multiplied with any value, let's say x cubed, as x approaches to, let's say, 2, then the answer should be something like b, which is 3, multiplied with the limit of what is inside here as a function. So that only means that we need to evaluate the limit here, that is simply x cubed, and then substituting these two, so we get 2 cubed. So that is 3 times 8, so we get here 24. Okay, so you can actually just never mind this b here. The thing is that you just need to substitute 2 here and you will get the same answer. Okay, and then for some more difference, these are just basic properties, and I don't think I have to like give an example for this. If the limit of f of x plus minus g of x, you can just simply separate these two by the operation, and then the answer is L plus or minus K, and that's how it goes for this one. And then for product, then the answer should be the product of the limits, and then for the division, it should be that the answer should be the quotient of these, or the quotient of these two functions that are being evaluated. And then for the power, if you have a limit of f of x, and then n is of course a set of n has a value of any number, any real number, then you could just simply have the limit of f of x and then raise it to a certain value of n, being it a positive integer. So with that, let's try solving this example here. So in this case, if we would look closely at the limit of 3x squared minus 4x plus 7 as x approaches to 3, what we have here are a lot of properties that we have mentioned before. So if you're looking closely, it is separated by subtraction and addition. So in this case, we can actually rewrite this. I'll just be doing this for now, okay? So we can actually rewrite this as the limit of 3x squared as x approaches to 3, and then minus the limit of 4x as x approaches to 3, and then plus the limit of 7 as x approaches to 3. And then this obeys the second property, which is a summary difference. And with that, let's evaluate the first term, the limit of 3x squared, which we will evaluate based on the scalar multiple. And remember, if we have something like that, that is simply the limit of 3x squared as x approaches to 3 is equal to 3 times 3 squared, which gives us 27. Okay, so with that, in the first term we have 27. Now we evaluate the second term, that is simply substituting the value of the limits. So what we get here is based on our something like scalar multiple again. So what we get there is 4 times 3, which is equal to 12. And then for the last one, what we get there is the limit of 7 as x approaches to 3. So remember, this is like a constant function, so the answer should be 7. So with that, we can now evaluate 27, 12, and 7 based on the operation that separates them, or each limit. So what we get here is 27 minus 12 plus 7. So the answer should be 22. Okay, so let's just check. It should be 15 plus 7, so 22. So we've obtained the correct answer. So I've done that just to show you how it works for this kind of functions, and it says here that this direct substitution property is valid for all polynomials and rational functions with non-zero denominators. So in short, what we're saying is that if we are given with any kind of polynomial function that has a non-zero denominator, and of course disregarding all the discontinuities, you will always have to just like substitute the value of c to that function, and then you will obtain the limit of that function. You can actually solve this using a shortcut by simply substituting the value of 3 here. What we get is just 3 times 3 squared minus 4 times 3 plus 7, and then what we get is 22. So that's how easy it is for polynomial functions when we evaluate limits. Now I hope you understand that. So now let's move on with the next property. So number 3, the limits of this is what I'm talking about before, the limits of a polynomial function and rational function. So I won't be dealing much about this now, but let's just try to solve for this. So remember, if we are given something like a polynomial function and a rational expression or function, we can just simply substitute the value of c here. So with that, let's try solving it. The limit of x squared minus 2x plus 3, and then divided by x plus 1, and then x approaches to 3. So with that, let's just substitute the value. So what we get here is 3 squared minus 2 times 2 plus 3 plus 1. And remember, the only restriction that we could get here is that if x is negative 1, then we will have a zero denominator, and since it is not, then we can just simply substitute. So the answer here is 9 minus 4 plus 3 all over 4. So what we get here is 9 minus 4, 5 plus 3 is 8. 8 divided by 4 is actually, I'm sorry, I made a mistake here. So this should be 3. Okay, so with that, this should be 6, and then 9 minus 6 is 3, and then plus 3 is 6 over 4, and which is equal to 3 halves. Okay, so that is how we solve for the rational expression. Fairly easy, right? So with that, we've got no problem with polynomial and rational functions. Now let's try evaluating some more of these as we go on to some other properties of our limits. So the limit of a function involving a radical. So what's good about this radical is that you can just simply substitute the value of c from our radical. So as you can see there, what we did was just simply substitute the value of x, the value of x as it approaches to c, which is c, and then the answer is the nth root of c. Okay, and then let's try having some more of these these properties. The limit of a composite function. So if f and g are functions such that the limits of g of x is equal to L and the limit of f of x is equal to f of L, then the limit should be given like this, as you can see here, and then the answer should be f times L. Now I will give you an example for this, but before that, let's just evaluate this first. This is an example for number 4. So what we need to do here is just simply substitute the value of 2 here. So that's how it goes for that. That's very simple. So we could get something like the cube root of 2 times 2 squared minus 4 times 2 plus 8. So you can just use your calculator to evaluate it, and the answer should be like 8 minus 8, which is 0 plus 8. So that is the cube root of 8 is simply equal to 2. So that is correct. And that's how easy it is also for the radical functions. Functions that involves radical. Now let's try giving some example for composite functions. Now when we talk about composite functions, then we're always referring to values, or two functions. So let's say we have f of x, this is equal to, let's say, 1 over x. And then let's try to have some more. G of x is equal to, let's say, x squared minus 7x plus 1. And then if I wanted to ask you, what is the limit of f g x approaches to, let's say, 2. So in turn, if we have this composite function, we can simply rewrite this as the limit of f of g of x as x approaches to 2. And this makes sense for this part here. Okay. So with that, let's just simply substitute the value using this composition of function. So what we get here is that we need g of x and substitute this g of x to the expression that is in f of x. So with that, 1 divided by x should be substituted with the function g of x. So with that, we have x squared minus 7x plus 1. And with that, let's just simply find the limit by simply substituting the value of 2 here. So we get 1 over 2 squared minus 7 times 2 plus 1. And what we get here is 1 over 4 minus 14 plus 1. So that is equal to 1 over negative 9, I think. So with that, so you could just simply write negative 1 over 9 in that case. So this is the answer for this problem. For the composition of function. So remember, you're just like doing something in your senior high school days of using this composition function, right? And just substitute the value of your x here. This kind of limit. And I'll just erase all of these. Sorry for the lack of space. Now let's try this number 6 here. These are the limits of trigonometric functions. So I will not be discussing more about trigonometric functions since we've already discussed about it. But as you can see here, the limits of sine x as x approaches c and all the 6 circular functions here, what you can see here is just simply that c here is substituted to x. Okay, so whatever value that we have, whatever equation that we have, for as long as it is trigonometric function, you can just simply substitute the value of c. Okay, for example, let's just give an example. For example, I have the limit of sine 2x, okay, and then I wanted to like find the value of x as it approaches to pi over 2. So with that, let's just simply substitute the value of pi over 2 from our equation. So that is 2 times pi over 2, and that is simply equal to sine of pi. And sine of pi is actually equal to 0. So the limit of sine 2x as x approaches to pi over 2 is 0. So that's how it goes for the limit of trigonometric functions. And it's just the same as like our polynomial functions that we have discussed before. Now, this comes the more complicated one, and probably this it will be the one that you will encounter a lot in your learning of limits. Let me read this first. This is a function that agree at all but one point. So in Tagalog, ito yung function na okay sa lahat maliban lang sa isa. Okay? Let C be a real number and let f of x equals g of x for all x such that x is not equal to c in an open interval containing c. If the limit of g of x as x approaches c exists, then the limit of f of x also exists, and the limit of f of x is equal to limit of g of x. Okay, so that is easier done than said. Okay, that's how it goes for math. No, it's always easier to like express it in solving rather than reading it. No, so let's try solving one. No, now remember this function x cubed minus 1 over x minus 1. So this is something like a kind of function that agree at all but one point. So what do we mean by such kind of thing? No, it fairly means that it has an asymptote or something like a value that will make it undefined. What is that value in this case? That value is actually positive 1, because as you can see here, any value, I mean the domain of this function is that any value of x such that x is an element of real number, only that x should not be equal to positive 1. Because if we have, let's say, positive 1 here, we get 1 cubed minus 1 and then 1 minus 1. What we get here is just 0 over 0, which is an indeterminate form. We can just simply say that, you know, the answer is 0 because it is actually not 0. 0 over 0 is an indeterminate form. You can't evaluate it. Okay, so with that, it agrees at all points but not 1. Okay, and how do we find the limit of those expression? So what we do here is what we call the redefining of an equation. So when we say redefining, we need to somehow redefine the equation by expressing this in terms like giving all the factors, or simply like having it I'm doing a squaring of the roots, or probably finding its conjugate. So things like that. Those are the things that we do in redefining. And what I'm referring to about redefining is that all those skills that you've learned in your senior high school about redefining will come in handy here. So now in this case, let's try solving this. Okay, so with that, let us try to redefine our equation by taking all the factors that we can get here. X cubed minus 1 is actually factorable to x minus 1. And do you still remember your factors for x cubed minus a cubed? So what we get here is x minus 1, and then we continue x squared, and then so that is x squared. Sorry, that should be x squared. And then since this is negative, the one that is in the middle should be positive. So that is positive x. And then the last one should have a value that is of the same, that is of the opposite sign for our constant here. So we get here positive 1 as well. And then with that, we can just simply divide it with x minus 1. And then by this redefining, what we can have here is that we can cancel out x minus 1 and we're left with x squared plus x plus 1. And finally, if we would substitute this to our limit, remember our limit is this one, and then we could just simply say that this is equivalent, or this limit, this expression is equivalent to the limit of x squared plus x minus 1 as x approaches to 1. In this case, it should be plus. So in this case, we just have to substitute this since this is already a polynomial function, and what we get here is simply 1 plus 1 plus 1, which is equal to 3. And this is actually the answer for this equation. So we did something different here from our previous ones, because as you can remember, all that we have done here is just simply substituting all the values of our c here, which is at which x approaches to that certain value, and yes, from 1 to up, at least up to number 6. And now what we did is redefine the equation. So in cases where you will get indeterminate forms, don't stop by just simply saying that the limit does not exist, but try to redefine the equation if it is possible. Okay, but if it is not, then you can just simply say that the limit does not exist. So for example, I have f of x, and then let's try to have something like x minus 4 and then x plus 2, and then the limit x approaches to negative 2. So with that, if we wanted to substitute negative 2 here, what we'll get is negative 6 over 0. And negative 6 over 0 is actually undefined. It is undefined. So, and if you want to like redefine this, you can actually you can't possibly factor out something here, because technically we don't have any factors for x minus 4 because it's already linear. So with that, the limit does not exist. Okay. So I hope you've understood the difference between these two. It's just that if it is possible to redefine, then redefine, do it. But if it's not, then, and you can't do anything about it, then just say that the limit does not exist. Okay? And you will encounter a lot of these limits when, this redefining things when we get further to the lesson. Okay, and there is also another property here. I want to unlock it, so I'll be removing this. I hope you've understood this part. Okay, so this one is the concept here is like I'll just be graphing it so that you would understand it. The squeeze theorem or the sandwich theorem. So when we talk about this theorem or sandwich, this squeeze theorem and then or sandwich theorem, remember we've mentioned about these kind of limits that do not exist. This one, the oscillating, or the function that oscillates between two fixed values. Now let's try, for example, we consider such kind of function to express this squeeze theorem. Let's say we have f of x is equal to sine 1 over x, and we need to find the limit of f of x as x approaches to 0. In this case, f of x is sine 1 over x, and that is an example of oscillating function. If you just wanted to try to find the value of this, you won't get any answer, and the answer here should be it doesn't exist. But if you just try to have here g of x, and this is another function, let's say x squared sine then 1 over x. So this is our new function. If I need to find the limit of g of x as x approaches to 0, what we get here is just let us try to solve it based on our understanding on our previous examples na isa-substitute lang natin tong value here. So we get 0 sine 1 over 0, and it doesn't have any value. Remember, sine of 1 over 0 is actually sine of undefined. How do you sine something that is undefined? So with that, this is not, direct substitution is not applicable for this case. So what we'll do here is just we will apply the squeeze theorem or the sandwich theorem. So remember, sine 1 over x is only restricted to values that are, if we have f of x such that it is sine 1 over x, what we'll have here is that sine 1 over x will only have values that are greater than or equal to less than or equal to 1, and then greater than or equal to -1. That's a basic rule of sine 1 over x, or any kind of function that you need to sine to apply the sine function, because the highest possible is just 1 and -1. So whatever the values here is just come in between these intervals. So with that, we have x squared. Now it says there that if you have a squeeze theorem, you can actually, since we've discussed all about the product rule, we can also say that if this function sine 1 over x, we represent this as f of x, and then let's try to have h of x being x squared. So we could simply say that before, based on our rule in product rule of our limits, it says here that if we have f of x, g of x, that is equivalent to L and K. So with that, if I wanted to find the limit of h of x as x approaches to 0, that simply means that I would have to take the limit of x squared as x approaches to 0, and the limit of x squared as x approaches to 0 is simply 0. So with that, I have the limit of h of x. And then if I need to find the limit of this one here, I would simply get any value that could mean less than or equal to 1, and then greater than or equal to -1. So with that, I can simply say that that is 0 multiplied with any number here that is greater than or equal to 1 and less than or equal to 1. So with that, the answer should be 0 times any number that would satisfy the condition here, and that is, let's say we have n here, and that is equal to 0. So in this case, we have solved for the limit of g of x being equal to 0, since it is x squared times sine 1 over x. So I hope I wasn't too fast describing it or explaining it, but to give you the how it looks like. So this is how it sandwiches from x squared, and then we just wanted to provide the oscillations for sine x, so it's something like that, and then it goes something like this. So as you can see here, it converges, or it sandwiches I don't know if there's such kind of verb, but it actually converges into a singularity here, which is 0. So that's how it goes for the squeeze theorem and the sandwich theorem. And this theorem is actually the basis. It is the basis for finding the special trigonometric limits that we have at number 9. So I just want you to remember this too. We don't have to solve for this or derive the function here. So just remember, the limit of sine of x over x as x approaches to 0 is equal to 1, and then the limit 1 minus cosine of x all over x as x approaches to 0 is equal to 0. So probably for some time we'll be solving this when we've reached the latter part of this subject. But for now, let's just leave it right there, this expression. And now let's try solving this one, okay? So if you wanted to solve this, we will be needing this basic property here. And remember, this is only applicable if it is sine x over x. And what we have here is sine 3x over x. So what I'll be doing here is I will redefine this function, okay? When we redefine, we're making the expression sometimes a lot simpler and easier to evaluate, but we're not actually changing that equation, okay? So I will redefine this by simply multiplying 3 here at the top and then dividing this by 3. So remember, this redefining didn't actually change our equation, because you can just cancel this 3 out and we're left with the same equation. But for the sake of redefining, I will be doing this now. And then based on our scalar multiple, I can just write 3 outside this limit function and then evaluate what's left here. That is sine 3x over 3x as x approaches to 0. And doesn't this expression look familiar with this one? So remember, if you have like sine x over x, that is always equal to 1. That the same thing goes for sine 2x over 2x, sine 3x over 3x, sine 4x over 4x. So that is 1. So this technically means that this is 3 times 1, 3 times 1, and that goes for our answer, which is equal to 3. So that's how it goes for our for this example. So remember, just manipulate the given and you will be able to find the answer for those things. And limits are actually easy for as long as you know the rules, you know all the properties that we need to apply in each kind of problem. And remember, those cases where we don't have any limit, and those cases where we can actually do some redefining and then find the value using that redefined equation. Okay, so don't forget these limits, and because if you've already mastered these limits, you will be able to like easily understand what continuity is. And for the just for the sake of giving you some like inspiration or motivation, continuity is a very easy topic. Okay, it's just something like a definition of what a function, of how a function becomes continuous and how it becomes discontinuous. So there's not much more about like solving if it's really continuous or not. It's just by sometimes just by looking at the function and then just being familiar with all the functions that becomes discontinuous. But then again, I will be having that on our next tutorial, since this is becoming quite too long for just one topic. So again, we'll be having continuity, and for the problems that I will be solving, because these are just examples, very basic examples, I will be giving you a separate lecture or video tutorial for those problem solving types, where I will just be solving a lot of problems continuously for limits and for continuity if possible. If it shouldn't be if possible, it is actually, it should be done. Okay, so probably I will be solving this module assessment. Hopefully I could get all of this in just 1 hour with 25 of this, but I don't think I can, because based on experience, we can only solve like at least half of this in just 1 hour, because I have to like explain. And with that, probably you just try to solve it at your home if something is left out here. But I just wanted to remind you that the assessment or the module assessments that I will be giving you, those that are required to be submitted, will be posted, or I will have to like give some announcement, a formal announcement for that. So if I don't give you something like an announcement or just a chat in our Facebook group or Facebook Messenger, then you don't have to like answer all of this and then submit it to me. Okay, it's just uploaded there for your review. Okay, and I will be uploading the consolidated module from the Faculties of General Engineering at Main 1, so you might as well want to take a look at it and review it for your practice at home. Okay, so with that ends our discussion for limits. I hope you have understood this kind of topic. There's so much more to take in for just 1 hour, I think, and it could have been better if we could just give some kind of more problems, but I think the video's getting too long, and yeah, you're getting tired. So yeah, that's all. Thank you, and stay tuned for the next video that I will upload. Okay.